Good afternoon and good evening, everyone, from wherever you're joining us. And welcome to our webinar series, Experts Speak, in association with IABAC, the International Association for Business Analytics Certification. Let me start by giving you a brief about the speaker for today, Mr. Spandan De. And Spandan is a research scholar at the Indian Institute of Technology, Kharagpur, and his area of research is speech signal processing, and he's currently pursuing his research on spoken language recognition systems, and his master's thesis is based on sound source localization. And today he'll be covering the topic on multilingual front ends in speech AI, challenges and opportunities. And just a request to all the participants, please post your questions in the chat and in the Q&A session, and we will present them to the speaker at the end of the presentation. Over to you, Spandan.
Thank you, Ram, and hello, everyone. So I'm Dr. Spandan De. Just a slight update. I am not present for a research scholar. I was a part of research scholar in IIT Kharagpur. Now I have joined as a lead engineer in Samsung R&D Bangalore, India. So now this topic, spoken language identification, it has been my PhD research topic. So I have been exploring this field from 2019. Now here as an industry developer as well in Samsung. I'm also working on related fields and even beyond those from different applications as well. So this is a brief about who am I and why I'm eligible to talk on those things. So let's begin today's session, which is multilingual front ends in speech AI, the challenges and opportunities. So we will start with our daily life, the speech AI applications that we usually it's a part of our daily part, even though we do not categorize them as speech AI applications, but actually, if we think sincerely, they all start from our voice commands. Now, when we talking about voice commands, earlier we used to text and convey our messages or search all those things from textual typings. Now, as per a Forbes India study that was conducted in 2020, already at that time, which was 5 years back, they surveyed that more than 50% of web search has migrated to a voice command based mode rather than textual typing. And we can say it's 5 years old statistics. So now this number has even risen, and the speech interface also evolved in 5 years. So we can say that in many cases, we are now gradually becoming more and more habituated towards just click the mic button on the search bar and speak to whatever we would like to explore. Now that shows itself that the human to computer or human to machine interaction, the mode of interaction has already been skewed towards verbal or speech based commands rather than textual commands. Of course, there are many occasions where we still prefer textual typings, but for most of our daily life, even if we speak with the machines, it is absolutely fine and even more convenient. On this line, I would like to mention about popular voice assistants such as Siri, Alexa, Bixby, all of them. If you observe, gradually they are now more and more proficient to listen what you are saying, comprehend in what it is your intention or the meaning of your verbal communication, and then they can also talk back to you or take the actions that you want. Even if you observe ChatGPT or the different Gemini, different popular LLMs that are becoming the headlines in nowadays, earlier days, even 2 3 years back, you were mostly confined to talk to them by typing in text. So you wrote something in text comments and something came back as text. But now gradually, day by day, if you observe those who very frequently use them, the speech interface with the LLMs are now becoming more and more efficient, and they are like the by default modes in many of the way how we interact with LLMs. So all those instances signify that we as a human give speech input to many AI applications in our daily lives rather than textual typings. So all those examples like voice assistants, LLMs, they work on some basic speech AI principle. So that basic working principle is I am shown next in the block diagrams. So if we start with, suppose I have a mobile phone, I would like to ask that what is the address of certain road. Now when I give the speech command, so speech is basically an analog signal. It is a when we speak something from our vocal tract systems, it is a basically variation of sound pressures. That variation of sound pressures, or that the variation lies in a frequency that is audible to our ears. Now, usually we have the input processing module. The first thing is a sensor or a microphone that captures that analog or the physical thing, which is basically a sound pressure variation, into digital signal. So that microphone captures the analog real world physical thing into digital domain. This is the first gateway to digital domain. After that, most of our AI algorithm that we are talking about, they are not readily, like we cannot directly feed those audios, or like due to computations or information extractions, there will be many issues if we directly put the speech to the AI algorithm. So we need this input processing module. So what does it do? In a very simpler terms, it converts analog signal to digital audio, and then it further converts that digital signal into some more processed form, so that the AI algorithm can easily process and understand. In technical terms, we call this thing as feature extraction. So this speech is now converted into feature. It is the feature that can be the input of the AI algorithm. Now, this AI algorithm, whenever it receives the speech feature format, it can be, where the magic happens, it can be modeled to do many different technical things. For example, this AI can be used for generations or generative AI. For example, if I say that to my LLM, that give some information about global warming. Now the AI will process the input, it will try to understand what is being spoken, and it will try to generate something in speech or text about global warming. This is generative AI. Another kind of speech AI, which we called the deterministic or classification based AI, where suppose I given someone speakers, and the job of the AI algorithm is to classify whether it is me or someone else. Or when I'm speaking something, the job of the AI algorithm can be to identify the emotions of my speech. So basically, it is the AI algorithm for the decision kind of AI algorithm. Their job is to make some category wise classification or decision based on the input speech command. A recent extension of speech based AI algorithm is into the emerging agentic world, where we will take some actions. The AI algorithm will take some actions based on the speech command. So suppose I tell that open YouTube. So the AI algorithm will process it. It will understand the meaning of what I told, and then it will open a browser with YouTube open. So it will also take some actions on behalf of you. If I say book railway ticket from source to destination on XYZ date, it should take the meaning and it will take the actions. So as I told, the speech AI algorithms in conventional studies, they are mostly, if you follow textbooks, mostly they are categorized into generative algorithm and classification algorithm. But very recently, they are also agentic domain of speech algorithm as well. So these are the technical categories in which speech AI has its span. Now, this is the skeleton, this block diagram or whatever I told. Now, under the same skeleton, what are the different applications that we can think of that we actually use? So the first application is audio captioning or speech to text. In technical terms, we call it automatic speech recognition. Whenever we observe some video streaming website, we can observe that real time also, or sometime offline, whatever someone is speaking, the text is coming at the bottom hand. Or suppose we are having a conversation, and this entire conversation nowadays, it can be saved as a transcript into the logs. So all those things basically convert speech. It takes speech as input, and it will give the whatever the transcript as output. Another very important speech AI application is voice biometry. I have a door. When I go to this some module of the door, some lock system, and I told open the door, the voice module, the biometric module will understand that I am the legitimate owner of this house, the registered speaker in this device. And once it verifies that my identity is original, it will open the door. So this is the automatic speaker verification, and associated with it, another emerging topic, which is deep fake detection. That is also an AI algorithm, like voice cloning based or text to speech based algorithm. It can happen that from the same door, someone used some voice cloning TTS and played it from a device, and the door gets open. So the voice biometric now also needs to identify who am I, as well as whether it is an biologically generated voice or someone has manipulated with my voice. This is also another important application of speech AI. Now, when we use different headphones or different sound boxes, we have noted this term as noise cancellation, echo cancellation. So this is also another kind of speech signal processing, and nowadays speech AI algorithm, where the main job is to take some noisy speech as input and make it a cleaner version of speech. So we will keep the speech part as it is, but we will remove the noise part. Another very important thing which is also now emerging is language acquisition based thing, like speech to speech translation. So it can happen that I went to suppose some foreign country or some foreign province where the native language I don't understand. So when I speak in my own mother tongue, on my native language, real time, the speech is converted into some translated voice into that destination language. So this is also now becoming very popular. If you follow some very renowned global travel blogs, you can see that people nowadays are actually on their blogs using such devices to interact with people from different countries and to connect with them. There is another very important application of speech AI, which is speech pathology. It means from the input speech, can we detect and model the somewhat of health abnormalities or some health conditions such as Alzheimer, stuttering, dyslexia, all those things? Can we identify them, or can we like identify what severity they are? And now people are also use them as monitoring benchmarks to for the treatments as well. So it's not only about disease detection, but also for the treatments as well. The last thing, which is now the most popular among all the speech applications, which is multimodal LLM, which is suppose I have a speech command, it converts speech to text, then the text goes into reasoning, and then it takes some actions or it generates something and it goes to text to speech. Or it can be entirely speech to speech as well. So different kind of, if you observe the literature, if you observe the blogs, these are the different kind of speech AI applications that we deal with daily life. Now, whenever we think about these things, one thing comes very clear is that if you want these all those environments of speech AI applications, the emerging things, to be accessible to a global audience, it is very important that we put one more very important cherry on the cake, which is the ability to take all these actions into multilingual conditions. It should not be confined to English or any particular language, but ideally, irrespective of whatever language my input speech command is, the processing, the algorithm should work efficiently. So that is the most important part for developing speech AI, that is enabling multilingualism into speech AI applications. So for this, uh, we need to first understand why it is important in a more detailed way, why it is important to have multilingual speech applications, and on a broader technical perspective, how we can achieve this multilingual effect into the applications, like how the AI applications will understand different languages and will reply back in different languages, all those things. So first, let me discuss a bit about the why part of these applications. Mostly when we have those, we use chat GPTs or any AI applications, usually we have a feeling that all those things are mostly in English or Mandarin or some very limited number of global languages. So unfortunately, this is quite true till a date. And that thing becomes more pronounced if we observe that there are actually more than 7,000 languages in the world. And even if we check like what are the most popular span of languages to the common AI devices, that number would hardly fill up to like even less than 1% of all those things. So you can understand there are so many languages in the world where this digital technology advancement is very limited. And even many of those languages, as I told, have wide number of speakers as well. So if we want to enlighten the global population with the flavors of technology, modern technology, if you want to make all those applications accessible to all sections of population across all the nations, it is very important that we took very serious focus on developing the or extending those algorithms through multilinguality. It can also happen that some people knows multiple languages and different applications, they are more profound in using different whatever the choice of languages. With this, if I say that 40% of the population are monolingual, so in that case, I can understand that mostly they will be using one language as their primary mode of communication. 43% are bilingual, 13% are trilingual, and there are some polyglots as well. So you can understand that for a same speaker also, it can happen sometimes. Suppose when I am talking in some professional environment, I may be using English. When I'm talking to my family, I may be using Bengali, which is my native tongue, or I can talk to my friends who are in Hindi. So different kind of scenarios are there. So we also need to accommodate for the same speaker also conditionally different languages. Now, linked with this social cause, there is also lies a very big commercial opportunity. Is that when we extend our product or our services to multilingual speech inputs and outputs, we can reach up to a much vast and diverse market base. And it will not only like numerically, it will increase the reach of our product, but it will also make it stable. Because when we have spread across the globe our presence, the ups, downs will nullify and it will give stability to our product as well. Now, it has, when we talk about multilingual speech applications, it has also helped in modernizing the classical linguistic studies as well. Many of the linguistics algorithm, for example, our languages, they can be classified into syllable timed and stress timed. When we are talking about syllable time languages in terms of linguistic definition, we said that each syllable that we pronounce from our speech has equal duration in syllable time languages. Most of the Indian languages, like French, these are syllable time languages. Stress time languages, they have unequal like syllable duration. Some syllables we pronounce with more emphasis, and those syllables usually the energy becomes higher, but the duration becomes shorter. So these are the linguistic definitions, but those definitions were not verified until we come up with signal processing and AI algorithms. We calculate the duration, syllable durations, we plot the distributions, and we come up with some classification cues that whether some language is really syllable timed or really stress timed. So many of the theories are also now verified and advanced with the AI and signal processing applications. So these are the whys why we should take this multilingual speech application seriously. Now coming to the how part of the slide. How can we let the model know that I am talking now in English or now I'm talking about now in Arabic? So how the model will understand? So if we trace back to the previous slide, we just included one extra front-end block. So for example, I'm giving an illustration of multilingual support in automatic speech recognition. So it means whatever I will say, the written format will be outputted. Now, as I told, my input speech command is there. There is a processing module which makes the speech into features. Then there's the hack. We will put a simple front end block before any backend applications. For this example, the backend is ASR or automatic speech recognition. So that front end is called spoken language identification. So usually it happens that I have suppose an English ASR model, automatic speech recognition model. I have an Arabic speech recognition model. Now this spoken language identification front end, it will take those input speech feature and it will try to predict what is the language being spoken, whether it is language one or English or language two, say Arabic in our example. Now, if the LID models predict that it is language one, then the corresponding backend for language one will be activated, and this flow diagram will deactivate this ASR for language two. Or suppose when I'm speaking in Arabic, it activated language two, it predict the LID model predict as the second language is being spoken, then I will simply switch off the connection to the ASR for the language one. So basically, this spoken language identification, it is a decision module, decision kind of AI algorithm that we insert as front end before majority of the multilingual speech applications. So the summary is most of the times for development purposes, we will have dedicated language wise AI algorithm, and a spoken language identification will decide based on our input speech command which of those language specific applications will be activated. That is how this is the most genuine approach of enabling multilingualism into speech AI applications. There are some variations of this thing as well, but this is the overall the key foundation of how we can extend to multilinguality. So this LID blocks is the main focus of this presentation. So we will first briefly discuss the technical overview of LID block. Of course, I will not go into very much into details, but it will give the discussion will give you some understanding about how things go behind when we try to develop LID systems. So again, the block diagram is further extended from slide 1 to slide 2 to this slide 3. So this input speech command, whenever we say, we use some data pre-processing, like we remove the silences, we slightly increase the volume so that it becomes more match. We can somewhat remove some noises and keep only the speech part. Then we, as I told, most of the AI algorithms, they are not ready to directly consume the audio. We convert it into some features or more mature and compact representation of the audio. So those features then fed to a classification head. This classification head, its job is to classify. Suppose I decided to train a 10 class language identification model. So I will collect some utterances or some audios from all those 10 languages, and I will have audio and I will have a ground truth level. Suppose audio 1 Hindi, audio 2 English, audio 3 French. Like this, I will have a database. Now I have this database. So now I have feature 1 Hindi, feature 2 English, feature 3 French. Like this, I have a feature. So X is the feature and Y we called the label. So this feature and this level is fed to the classification algorithm. So it is a class of supervised AI algorithm because we are providing the human level as well. We are telling that, okay, this is this class, this is that class. Now your job is to learn and predict for unknown audios. So if I take the example of 10 class LID, it will try to, whatever the speech input will have, it will try to give a 1 cross 10 class vector or some 10 numbers. Each number gives the probability of that particular languages. So that is called the prediction scores. So suppose the model says that 90% I am sure that this is Hindi and 10% I think this is English. So it will be 0.9, 0.1, then rest all the numbers are zero. So this is called a prediction score. Then whatever language will have the maximum prediction score, that is the predicted language. For this example, we'll say that the predicted language is Hindi. And then this LID model will activate the Hindi ASR or Hindi translation module, whatever is that particular language's algorithm, backend algorithm is there. So we can understand two main building blocks are there in this LID thing. One is the speech feature, or like in which format we will put the input, or how we can convert this raw audio into some sort of format which the AI algorithm, it will be easier for the AI algorithm to process. And the second thing is the AI algorithm itself. So if you observe the LID literature, so there can be different ways or different kinds of features from the audio speech. One thing is acoustic phonetic features, which is the most common thing. So if you observe this pyramid type of structure here, this is a hierarchical overview of speech features. So those which are in lower, they are called low level speech feature. It means easily with some basic mathematics, we can compute those features from directly from speech. And those who are at the top of the pyramid, they are called high level features. It means we need to have more sophisticated mathematical model to get all those features. So it means the lower level features are easier to extract from speech and the higher level features are difficult to extract. But there is one catch is also there, that lower level features, they are assumed to contain less amount of information from speech, whereas higher level features, they are assumed to contain more meaningful information from the speech. So there is a trade-off. The lower level features, they are easy to extract, but they have less information. The higher level feature, they are non-trivial to extract, but they have more information. So from that engineering aspect, most of the time researchers still try to like take the acoustic or the lower level features as the baseline, because it has been found that we need to deal with a lots of audios in today's deep learning era. And if our feature extraction method is very like computation heavy, then it will take a lot more time to develop, and the amount of performance gain is not worth for the amount of time taken for using this high level features. So in most of the time, we use those acoustic features or the low level features because we can quickly get them and they end up to a very decent performance thanks to the different algorithms, the classification algorithms. So if I quickly overview the acoustic features, which are low level features, they basically give you the time and frequency information. It means at which time, what frequency is more pronounced, that information is present. In phonotactic information, it is basically the sequence of phonemes, or the phonemes are the smallest sound units, k, t, p, like this. So some sequence of phonemes that we extract and we fed it to the classifier. Prosody feature is very interesting here. It gives you the intonation, like how our pitch is varying, the rhythm, how fast or how slow we are saying, the stress, all those kind of, I would say the paralinguistic information is called prosodic features. And lexical or syntactical features, they are basically the meaning of that word. Suppose lexical is the individual meaning, or syntactical is the grammar, all those things. So these features are difficult to extract. So we stick to this time and frequency, or the acoustic feature, the lower level features with the classification. So let us assume we have extracted one of those acoustic features. Now we are putting it to the input of the classification module. Now I will not go very much detail into the classification module, but in the bottom diagram, I have told that how through the course of time, the different classification AI algorithms have evolved in the speech processing literature. Earlier, they used hidden Markov model in the 70s. Then till up to 2000, the Gaussian mixture model, or GMM, those things are profound. 2004, around that time, if you observe the papers that come up for this field, support vector machine, or SVM, were very much popular. Then this deep learning, or today's era of AI, around 2014, at the time, you can observe that majority of the LID papers, spoken language identification papers, they're in deep neural network. Now this X vector, these foundation models, they are just larger and larger neural network, or deep neural network. So in today's era, if you observe the foundation model in 2021 onwards, they have hugely large amount of computational structure. So it means these models are huge, and they also need to be fed with a huge amount of training data, so that they can give you a very good, even better than human level performance for this LID class. So I will suggest the audiences to go through all those classifier paradigms individually, because this is beyond the scope of those presentation. But now we are in the era of those X vector, or this foundation model. This is the current state of the art. And this is a bit technical slide about the feature extraction, the low level feature extractions. One of the example. I will not go into very detail of this, but just a very overview how this raw audio is converted into this low level time frequency feature. So the stage one is the voice activity detection. Suppose this is a speech waveform. Now first, the processing module identifies what are the spoken part and where there are actually silences. If you observe the red parts when I am not saying something, and the green parts is where I am saying something. So it will just slice out all those red parts, and it will only keep the green parts. It means when I am actually speaking something. This is called the stage one. Now, the stage two, we will cut the audio into small windows. Suppose 25 millisecond of windows I will cut, and I will shift the window by 10 seconds like this. And for each of these small window, I will extract the frequency content of those small window using discrete Fourier transform. Suppose mostly if we respect the audible range of speech, then this, for one frame, the discrete Fourier transform in stage 3, it will contain what amount of energy is present into what frequency component. So if you observe this stage 4 diagram, if we think that this x-axis, the left side is 0 hertz and the right side is 8 kilohertz, and if you observe this yellow line, so it shows that at what frequency, what amount of energy was present with that particular 25 millisecond of audio. Then we multiply this frequency information with something called MEL filter bank. As I told, this MEL filter bank is inspired by how we humans process audio. It means, like, if we change some frequency from say 100 kilohertz to 105 kilohertz, our ears can easily detect that frequency has been slightly increased. It's a bit high pitch voice. But if we change that same amount of frequency from 1000 to 1005 hertz, our ears cannot detect that. So it means our ears are less sensitive to high frequency variations as compared to low frequency. In other words, we need to capture the low frequency variations much more densely as compared to the high frequency variations. So that thing is actually done by this MEL filter bank. So this frequency energy information is processed by the MEL filter bank, and at stage 5 we got another output where the lower frequency variations are much more enhanced and the higher frequency variations are relatively compressed because that are not even audible to our human ears. It is not useful to feed them to the AI as well. Finally, we apply some logarithm like to put the magnitude in a certain numerical range. And for all those frames, if you see the stage 2, each this magenta color is a window. So for each 25 millisecond, we actually have one column, one vertical column of this below image. So like this, for each audio, we have so many 25 milliseconds of window, which we call the frames. And for each frame, we have one column. So if you observe this beautiful diagram, which is called MEL spectrogram in stage 6, this is computed by stacking all those columns for all these 25 millisecond windows. And this x-axis is the time. Like the left side is suppose 0 second and the right side is the horizontal line, the right side is 10 second. And the y-axis is the frequency. Suppose the bottom left corner is 0 hertz and the top left is 8 hertz. So it means from this feature, we can understand if the yellow line, if you can see, these are the higher energy in certain frequencies. So we can exactly from a pinpoint, we can identify at what time, what frequency component has the most amount of energy. So this is the way, a very like a bit more technical actually, I would say. The input speech command is fed to the AI algorithms. This is actually much more easier for the AI algorithm to process as compared to raw speech. Of course, nowadays algorithms are coming which can directly take raw speech, and actually all these applications are inside to the AI algorithm itself. But still, in most of the cases, we manually extract those features and we feed them to the AI algorithm. So this is a bit technical. Let's not go into very heavy on it. So this is just to get some extra detail about the how we can the speech part of the speech AI applications. Now we will coming to the most important business parts of this slide, which is what are the major challenges that we face when we try to develop this spoken language identification or LID development. So, as someone working on this field for so many years, the main thing that I observe is when we try to develop a spoken language identification system for so many languages, the main issue is the issue of low resource. So what is the issue of low resource? It means we need to have some database for our AI algorithm where suppose audio 1 is Hindi, audio 2 is English, like this. We need to have some table. But it can happen, it is actually happening that in real world, we will have abundance amount of say English audios. But if we want to take some audios, for example, some say Sautali is a language in eastern and central part of India. If you want to develop that into LID system, we usually do not have that much amount of data in the digital domain that can be fed to the AI algorithm. So it means I want to develop a 10 class or say 20 class LID system. It will take any audio and it will try to predict among those 20 languages which one is present. But actually for out of those 20 languages, I have decent amount of audio for 10 audios, medium amount of audios for 5 audios, and for rest of the 5 audios, I hardly have any audio. So what will happen is that the AI algorithm by default, it will be biased towards that class who has more data. So it means our AI algorithm, unless we treat it in otherwise, which is shown in the rightmost corner, the AI algorithm will give less reliable performance on a broad section of languages. And that information is much more enhanced if I again recall that there are actually more than 7,000 spoken languages in the world, and some of them even have more than million speakers. It means economically and socially also they are very important, but we do not have enough very like valuable data for those languages. So, what are the repercussions of this issue of low resource? Obvious outcomes that are shown in the yellow blocks in the left side. The first thing is called overfitting. As I told, nowadays the AI algorithms, the AI capacity is so much larger that we need to put even large amount of data as compared to 5 years back. So the present AI algorithm we are very good, but they are very good because one of the factors is we need to put a lot of data into those. They are data hungry. So if we do not have that much amount of data for different languages, the performance will be even more biased. The second thing of limited data is called domain mismatch. Now, suppose somehow I am able to generate some Sautali language audio from some school, from some classroom environment. So this is so small, or we call this domain is so small that the model actually do not generalize for real world applications. For example, what are the domain? So when we are talking about language, which is the center violet color diagram in this, there are all those octagonals are domains. It means speaker, accents, room environment, the device of recording, the background noise, or when I am telling something around conversation, something, all those things. Ideally, all those factors should not affect the performance of our LID system. Suppose I am speaking or someone else speaking, the algorithm should predict equally. Whether I'm speaking in my some standard dialect or when I'm speaking in my native dialect, the algorithm should work good. Whether I'm telling this recording this using this AI device in some outdoor, I'm using it in some railway station, I'm using it in some classroom, in all those situations, the algorithm should work. So all those variables where ideally the AI algorithm should work, these are called non-lingual domains. So if we have very small amount of data of one particular domain, suppose I have the Sansari data only of some classroom, then it may not work when I test this AI algorithm into some outdoor environment. So it means we need to cover a diverse domain, different number of speakers, different accents, recording taken from different room environment, from different noisy conditions. All those kind of data we need to gather so that this domain mismatch is avoidable. And the third thing, as I discussed earlier, also inconsistency. If I developed a product and my product give reliable performance for certain classes of languages and it do not provide reliable performance for certain other classes of languages, then it will be an inconsistent product which will try to diminish the confidence of this product as well. So from all those things, this is the major issue of language identification, which is low resource. So what we can do for to deal with this low resource or we do not have enough data, that problem. So the first is obviously collect and label more data. But as I told, it is very challenging due to the geographical location of certain languages, the social presence, the economical conditions, the current political conditions, all those things. When someone needs to go record the audio, or we need to even collect from video streaming or audio streaming websites, but then some language expert needs to listen to those audios and predict, okay, verify that okay, this is actually from that particular languages. So this is a time taking, so there should be some hack as well. So what are the technical thing we can do? We can augment the data. Suppose I have 1 hour of data, Sautali, let's say example. Now I can add some sea beach noise or I can add some vehicle noise into this in a slight amount so that it feels like whatever was recorded in classroom is now recorded in front of some sea beach or in some railway station. So like this, I can increase my 1 hour data to 2 hours, 3 hour, all those things. I can use transfer learning. It means I have suppose for language A, I have a huge amount of data. I have a LID model for language A and B. Now, I will use that model itself instead of developing from scratch for language A, B, C. I will use that already matured model to to extend my LID model to the new language with less data. So I will not develop from scratch. I will use whatever was existing. There's also text to speech based synthetic data augmentation or cross corporate evaluation. It means whatever we system we develop, we need to make sure that we test them into diverse domain situations. We test them with different sections of people, different age groups, different accents, and then only we verify and launch our product. So these are some of the steps that we need to focus for low resource LID. And in literature also, various of these topics are already well explained. I will suggest the audience to go for the individual topic and explore. Now the last slide, which is what are the other challenges. Now this is my favorite slide because we all can connect with this slide. The first thing for LID development is the issue of code switching or code mixing. We are in a cosmopolitan world nowadays, especially in metro cities. People from different linguistic backgrounds, they work together, stay together. It means we very frequently change the language. We are not sticking to one language when I'm speaking. And but our LID AI algorithm, they are expecting that whatever is my input, the input is from only a single language. But actually, in that input, we are speaking one or two or even three languages as well. For example, I just given one example that I will call you later क्योंकि मुझे अभी बाहर जाना है. So you can see the two colored shades. So it means in a sentence, one phrase is from English and another phrase is from Hindi. So this is a classical example of code switching. Another classical example of this kind of language interchange is called code mixing. It means मेरा network connection अभी बहुत slow है. So this word slow is an individual word among a series of Hindi words. So where it is not a phrase, but individual words are interchanged with different languages. This is called code mixing. So this is one challenge the current research and development community of LID are handling. So they're handling it with a new domain, which is extension of LID, which is called diarization. It means who spoke which language when. So it will not predict just only the language, but at what timestamp what language was being spoken. Another issue with the current LID, as I told earlier, is the issue of dialects. So it is not necessary that we will be speaking with one dialect only. We need to cover different dialects as well. There can be another issue of mutual influence and similarity of languages due to historical reasons, geographical reasons, political impact. There will be language one which is highly influenced by language two. So my LID system can get easily confused between these two languages. So we need to figure out this issue as well. There are some applications wise challenges as well, like the LID system needs to be extended to those applications. For example, real time or streaming LID or language identification for children's speech, language identification when we are talking emotionally, or like multimodal thing, like I'm speaking something from my audio as well as from my lip movement also, we need to identify LID. If those information are available, then the language identification system will be much more efficient. So these are actually the developmental challenges. I am keeping some of those points as open-ended questions to think how we can develop or to motivate the research community to take up these as individual research projects and to contribute towards the society for this. So these are some useful references. I think these are mostly research papers which I found very interesting of this thing, of this topic. And yeah, so this is all. Thank you, everyone. Thank you.
Hey, thanks, Spandan. Uh, we just take some questions in the Q&A section, but a question from my side.
Hmm.
Uh, where do you think the biggest challenge is, like, which geographically, right? Which country, knowing that, like, where India is at, like, where we speak so many different
Hmm.
languages, our dialects keeps changing every few hundred kilometers. We have spoke different dialects spoken. So to train the models, like, I know there's a shortage of data, but then do you think this is where these models will have the biggest challenge in where in India?
Yeah, of course. Like as I told, India is the third most linguistically diverse country. It means so many. There are actually 1,500 Indian languages with
But the
22
first
official
two,
languages, and there are
we have
also
the third.
dialects. Yeah, and surprisingly, the first and second are smaller countries. They are Papua New Guinea and Nigeria. So that shows that for those countries, even the frequency is so much higher. If we go few kilometers, the language changes. So for all
I
those
like
countries, yeah, this is very, very shocking. I think we need to either, there is one straightforward approach, that is to collect more data. And another approach is to advance the AI algorithm using like some techniques like zero shot algorithms, few shot algorithms, where the model should not be reliable to consume a large amount of data. It should learn the most important characteristics from a smaller amount of subset of the data as well. So those zero shot, this few shot learning, which are evolving in the literature, I think they can be very useful in those dialects or those subtle variations in the languages as well.
Yes, let's take up a few, couple of questions. Like, we have one of attendee asking, like, how does AI figure out the difference between the language and then process it in real time and then give a proper answer? And yeah, I think you covered it, but can you just give me a couple of sentences to
Yeah. So one
in
thing is
real
very,
time?
very important. Exactly. This is a very good question actually. So when we are developing our AI algorithm, if you observe the research papers recently, we are always at, it's called convolution causal architecture. It means we will only look towards the left. If we are offline architecture, we will look at the left, we will look at the right with the time, and we'll consume the entire audio, we'll wait and we'll process. But when we are working for real time, suppose that I am at the third second, so I will have to predict my language prediction or whatever the prediction is from the information from third, second, and first second. When I'm working at fourth second, I will have some more information. So I will be having fourth, third, second, and first. So I will always look towards the left. My architecture is designed such that it will only consume from the left. It will not wait something from the future. And at that spot, it will give the prediction. Of course, the accuracy can be a bit less compared to left-right kind of non-causal algorithm, but this is the way we are working for streaming kind of thing or real-time applications.
We have another attendee asking, like, which languages are more challenging for speech than other? Any particular
Actually,
language spoken around the world?
there is no hard and fast answer. Suppose I am developing an algorithm, my data for language one is very clean, and my data for language two is both clean and noisy. Now, when I am testing my device, I got noisy data from language one. So in those cases, my perception will be that language one actually difficult than language two. But someone can have language two with clean data, and language one has both clean and audio and noisy data. So for that person, language two might be more difficult. So from this perspective, I will say it is more dependent on the data set, but collectively we can say some of the languages are very close to each other. For example, Hindi, Urdu, so or Bengali, Odia. So when we are developing for multilingual system, these kind of languages sometimes confuse with each other. So these closely related languages are the one which linguistically will give you more challenge. Otherwise, any language can be more challenging, depend on the characteristics of data you have.
Yeah, we have another attendee asking, how do different accents and dialects affect the model performance?
Yeah. So, for this example, I will say that there are actually no hard and fast definition of dialects and accents in languages, but still, it can happen that some of the dialect of a particular language is spoken into some border areas, some geographically or political border areas of some language too. So it can happen that this particular dialect of language one has much more essence of language two, like equal kind of effect of language two and language one. Or it can happen that that particular dialect is not at all completely understandable by all the native speaker of that particular languages. So in those cases, that those particular dialects become much more difficult to work with. On top of that, there is also accents. Accents are based on the different sections of people, and dialects are based on the different geographical sections of the people. So on those cases, if those kind of examples are not present in my training data, then accents and dialects can be very much degrading the performance. But if we try to collect even small amount of variations from the different dialects and accents, then probably we are on the safer side thanks to nowadays very efficient classification algorithms.
We'll take one last question. Okay, we have one of the attendees asking, can you put more light on how does a machine know the actual meaning of certain words
Yeah,
in terms of interpretation?
I think as I was discussing, there was a low level feature and there was high level features. High level feature means we need to capture more information. Suppose I am speaking something now if I have this smaller duration, this can be it can be like it can goes to different languages with the word sound so if I want to understand the word meaning, I need to stack those features. As I told, the frame wise the different features was there. I need to keep on collecting the features for at least 2 3 seconds or what some words is consumed, then the model can understand the direct meaning of that, implicitly understand the direct meaning of that word. Now if I want to go the contextual meaning, suppose I said that I am weak. Now this week can be calendar week, it can be my physical health as well. So in those cases the model needs to capture even larger it's called the context, even larger context. It needs to look for the left right words, the entire sentence as well, to get the correct meaning. So the simplest answer is we need to keep on accumulating more and more time domain information together so that few milliseconds become few seconds become say 10 seconds, and we can capture the actual that amount of length. So if we capture 5 6 seconds of audio together into feature, then the model can understand that span of information. If we give only 1 second of audio, then it is not, even humans can also don't understand what is the meaning of those things. So the simplest answer is accumulating more and more time domain features and efficiently putting them into the AI algorithm. The algorithm will then understand the meaning of this.
Hey, Spandan, really appreciate you taking time out, to give the session. It was very informative, and yeah, hopefully all our audience, found it, very, very interesting as well. And to all our participants, please visit our website iabac.org to become an ATP with IBAC, and we'll keep you posted on upcoming events by email or across our social media channels. Okay, and we look forward to connecting with you all soon. And thank you for attending today's session, and have a nice day, everyone. Have
Thank
a
you
nice day.
everyone. Thank you.
Bye.
Bye.